So today I want to talk about how charges moving in a magnetic field experience a force. We learned that moving charges, aka currents, create magnetic fields. And it's also true that moving charges in a magnetic field experience a force. And this is very surprising, really. Let's think about electric forces. Electric fields are created by charges. So a positive charge just creates an electric field. And another charge interacts with that field and experiences a force. Magnetic fields are created by moving charges, and they affect moving charges. And so as we'll see, if a charge is not moving, it experiences no magnetic force. It's a little bit surprising. So here's a slide to kind of demonstrate this. We see here that if we've got some charge here, here we see a charge. This arrow right here represents the magnetic field. So here we have a stationary charge in a magnetic field, and there's no force at all on that charge. That's interesting. How about this? We've got a magnetic field here, and we've got a velocity in this direction. There's also no force on this charge. If the magnetic field and the velocity are parallel, there's also no force. So that's interesting also. We see that when there's an angle between the magnetic field and the velocity, though, we do see a force. Again, it's a little bit surprising that the angle between the magnetic field and the velocity determines the force. That's crazy, but it's surprising, but it's true. So as the angle between the velocity and the magnetic field increases, the magnetic force also increases. And the force is greatest when the velocity and the magnetic field are perpendicular. So again, we get zero force for a stationary particle. We also get zero force for a particle that is moving parallel to the magnetic field. That force increases as the angle between the magnetic field and the velocity increases, and it reaches a maximum at 90 degrees. And so you can see here, we are necessarily in three dimensions again, because V, B, and F are mutually perpendicular. That defines three dimensions, which means that magnetic forces are fundamentally three-dimensional. Now, there's two options here, right? We've got a magnetic field and a velocity that are perpendicular. There's two ways that the force can be perpendicular to that. The force could either be up, as represented here, or it could be down, as represented here. How do we know which of those two options is correct? Well, we need a mnemonic to help us figure that out, and we have right-hand rule number 2 to help us figure that out. Right-hand rule number 2 is used for determining the direction of the force on a charged particle moving in a magnetic field. Recall that right-hand rule number 1 helped us determine the direction of, or the sense of, the magnetic field if we knew a current, right? So forces were not involved in right-hand rule number 1, but forces are involved in right-hand rule number 2. Right-hand rule number 2 works like this. We get our right hand out, and we make our three mutually perpendicular vectors by representing them with our middle finger, our pointer finger, and our thumb. And so there's a lot of different versions of the right-hand rule out there. If you go hunting online, you'll see a lot of versions of it. I'm going to stick with the representation that is shown in our textbook. It works quite well, I think. So in this representation, the velocity of the particle is represented by your thumb. The magnetic field is represented by your index finger. And of course, that means that the force is represented by your middle finger. So we align our thumb with the velocity, we align our pointer finger with the field, and then our middle finger becomes the force. Now, I have a mnemonic to help us remember that. Okay, so thumb is velocity. So this is like I'm hitchhiking, like I'm going somewhere. Woo, okay, I'm going somewhere, thumb is velocity. The pointer finger is your magnetic field. We're just going to have to roll with that one for just a second. The middle finger is the force, and we can remember F. Okay, so there we go. So we got our velocity, our magnetic field, and our force. Okay, so we have a velocity to the right. We have a field that is into the page, and so we see that the force must be up. Again, a velocity to the right, a field into the board, a force that is directed upwards. And so, using our right-hand rule number 2, we conclude that the upward direction is the correct direction for the force. Okay, it's a little bit tricky. It just takes some practice. Once you practice it a little bit, you'll find that it's not too bad. So here it is. And now we can add to the direction. So we use our right-hand rule to help us calculate the direction of the force. The magnitude of the force is given by this equation right here. So the magnetic force is the magnitude of the charge times the speed of the particle times the magnetic field, and then times the sine of the angle between them. And you can see that this encompasses all of the information that we had in those first few slides. If the velocity is 0, the force is 0. If alpha is 0, the force is also 0. If alpha is 90, that's the very largest that the force can be. Well, let's practice just a little bit using the right-hand rule. I think the equation there is fairly straightforward. It's really the right-hand rule that's tricky. So, what is the direction of the magnetic force on the proton in this picture right here? Why don't you pause the video and see if you can't wrap your brain around it, and I'll see you on the other side. Okay, so I've added a little picture here so that I can kind of work with it, and it helps me wrap my brain around it. I've got the magnetic field represented by these lines here. Right? So we're interested in the direction of the magnetic field at the location of the charge, right? Notice that the magnetic field at this point has a different direction than it does, say, at this point, right? So we're only interested in the direction of the magnetic field at the location of the charge, and that is to the left. So we've got a field to the left. We've got a velocity that's up or towards the top of the page. So there's our velocity. There's our magnetic field. So let's use our right hand. Velocity is represented by our thumb. So our thumb goes here. The magnetic field is here. That means that we have a force that is out of the page. Right-hand rule number 2 tells us a force out of the page. PowerPoint agrees. So we want to be careful using language like up, down, because up and down can mean either, if I'm looking at a piece of paper here, we might use up and down to describe up, down. We also colloquially could use up and down to refer to up and down the page. So we really want to be careful here, and we don't want to use the words up and down because it can be ambiguous. We want to use the words into the page, out of the page, top of the page, bottom of the page, left, right. Those are unambiguous descriptions of the 6 possible options there. Here we're saying out of the screen. Okay. Let's do another one. Here we see a diagram of a top view of an electron beam passing between the poles of a magnet. The beam will be deflected which way? Okay, so now I've drawn my picture here. We do have a velocity going towards the bottom of the page. Now we need to figure out this is an added step in this problem. What direction is the field in? And the field, of course, leaves north poles and enters south poles. So my field in this region is in this direction to the right. So that is my field, always to the right. Okay, so my velocity is down, my field is to the right. That gives me a force out of the page. But wait a minute. We have to be a little bit careful here. Because it's an electron, the right-hand rule works for positive charges. So what works for negative charges? The opposite of the right-hand rule. So here we have a velocity, a field, and the force out of the page is what our right-hand rule says. But it's a negative charge, so we flip it, and we say it is into the page. Okay, not too bad, but there's a number of things you have to remember, right? Not only do we have to remember the right-hand rule, we have to remember to flip it for the negative sign, and we have to remember that outside of a magnet, the magnetic field lines always point north to south. Let's just do another example. We've got another electron here, and it's moving to the right in a magnetic field that points upward. What is the direction of the magnetic force? Try it out. All right, so we've got a velocity, we have a field, a force out of the page. Oh! It's a negative sign, so we flip it. Velocity, field, force, we flip our answer. Our correct answer is into the page. Not too bad once you get practiced up with it. Okay, I want to take a quick break from magnetism, and I want to jump back and talk about physics 1 for just a moment. So let's imagine that I have a ball on a string, and I'm winging it around my head like this. And here's a top view of me swinging that ball on a string around my head. Here's the ball right here, and it's going like this. Okay, and let's say that the ball is, moving 10 meters per second, and everywhere it's moving 10 meters per second. Okay, so my question for you is the ball accelerating? So I'm winging it around my head at a constant speed. Is the ball accelerating? Well, some of you may have said yes, some of you may have said no. I suspect if you said no because it's at a constant speed. But we need to remember that acceleration is a change in velocity over a change in time. And remember that if the velocity is changing, then it is accelerating. And remember that velocity is a vector. It includes magnitude and direction. So in this case, the magnitude of my velocity is not changing, but the direction is. Well, it's a changing velocity. If we have a changing velocity, it is accelerating. So we need to remember that acceleration is speeding up, slowing down, or changing directions, turning a corner. In this case, we have the changing the direction or a turning the corner kind of acceleration. And you may remember from physics 1 that that type of acceleration is called a centripetal or a radial acceleration. And it always points towards the center of the circle. Centripetal means center seeking. So this ball is accelerating. The acceleration points towards the center of the circle. Now, recall Newton's second law. Newton's second law is really a cause and effect relationship. Usually, we write it as F equals ma. I'm going to write it a little bit different here. I'm going to write A equals F net over m. And in this form, we see Newton's second law as a real cause and effect relationship. The cause is a net force, the effect is an acceleration. The mass determines how much of an effect you get for a given cause, right? So, what causes accelerations? Forces do. And this is a vector equation. The direction of the net force is the same as the direction of the acceleration. Therefore, what is the direction of the net force on this ball? Well, in the same direction as the acceleration, the force is towards the center of the circle. So we have a force towards the center of the circle. That's what's causing it to accelerate. That's what's causing it to move in a straight line. And so notice then that the velocity and the force are always perpendicular. Recall that a force that is perpendicular to the velocity does no work. So magnetic forces do no work, which is a subtle point we won't get into too much in this class. Magnetic forces do no work, but they can change the direction of something. And so when we see an object that is moving with a constant force perpendicular to its velocity, that is an object that's moving in a circle. Okay, let's jump back and we'll talk about some physics 2, back to magnetism. Here we see a particle moving in a uniform magnetic field. Now, it's no different than what I have up here, although in this situation, the force that was causing the ball to move in a circle was provided by the tension in a string that I was winging it around my head on. In this case, the force that's causing the particle to move in a circle is provided by the magnetic field. So there's a magnetic force that is causing this particle to move in a circle. But whenever we see a velocity perpendicular to a force, we are looking at circular motion. And so if we have a particle that is moving perpendicular to a uniform magnetic field, it is undergoing uniform circular motion at a constant speed. Again, a force perpendicular to the direction of the velocity does no work, therefore it does not speed it up or slow it down, it simply changes the direction of the particle. So circular motion requires a force directed towards the center of the circle, as I was just saying. And so recall from physics 1 then that v squared over r is the centripetal acceleration, and so the force on some particle moving in circular motion is simply mass times acceleration, mass times v squared over r. We could plug in our formula here for the force on a charged particle and do a little rearranging, and we've come up with this equation here. So this is the radius of orbit for a charged particle moving in a magnetic field. What shows up here, the particle mass, the particle velocity, the particle charge, and the strength of the field that the particle is moving in. So in general, a charged particle moving in a magnetic field, its velocity may not be completely perpendicular to the magnetic field. In general, it will probably have a component that is perpendicular and a component that is parallel. This parallel component, of course, will not contribute to the force at all, because a particle with a velocity parallel to a magnetic field experiences no force. So the parallel component of this particle's velocity does not contribute towards its force. However, the perpendicular component does. So here's a top view of this same situation. Right? Here we're looking sort of at a side view. We've got the velocity going here. And now we're going to go ahead and look down the magnetic field. Looking down that magnetic field, we would see this circular motion, just as I was describing a moment ago. However, don't forget that this particle still has some component that is parallel to the field, which means that in this view, we see constant circular motion in this sense right here, in a clockwise kind of sense, and the particle is still moving towards us with this constant velocity parallel to the field. So, if we were to look at another side view, or another view here, we would see that the net result is that the particle moves in a spiral with constant velocity parallel to the magnetic field and circular motion perpendicular to the magnetic field. We could call this a helical path or a spiral path, and indeed this is the path that the charged particles streaming in from outer space follow as they get trapped by the magnetic field of the Earth and funneled into the poles. As they spiral around those magnetic field lines, they have collisions with the particles in our atmosphere, which slows down the charged particles, and it releases that energy in the form of electromagnetic radiation, which is the aurora here. So it not only gives us a nice show, and in the northern latitudes, it also helps protect us from radiation streaming in from outer space. So it's very useful for us humans.